Welcome. In this video, I wanted to talk about the idea of a bank curve and review how we apply Newton's second law in this context. Remember why we discussed the idea of a bank curve? It had to do with the fact that there's one particular kind of motion which is unique, and that was the uniform circular motion. And remember, in uniform circular motion, we had an object which was going in a periodic circle, and because of that, its speed was unchanging, yet the object was accelerating. So because the object had non-zero acceleration, we had to somehow account for that acceleration, because Newton said, at least according to his first law, the object's state of motion should not change. So according to Newton, things should just maintain a straight line of motion if they are in motion. It's impossible for them to change direction, that is, for them to accelerate, unless there's a force. So it is in this context, it is for this reason why we are able to build bank curves, because Newton allows us to account for this centripetal acceleration by taking care of the forces responsible for that centripetal acceleration. Okay, so in this slide, what I have is a picture of the overview shot. So imagine you have a car that's going around this circuit. This circuit has a certain amount of bank, that's the amount of tilt relative to the flat surface. So you might imagine this would be the flat surface of the earth, like the ground. And from the ground, the track is slightly lifted by an angle of theta. Now, the distance from the center of this circuit to the road is going to be r. And the object, which in this case is our car, is proceeding at a speed of, well, v, or velocity v. Remember, the magnitude of this is going to be fixed, but the direction is going to be all the time changing. When the car is over here, the velocity would need to be tangent, so the velocity would look something like that. And when the car is over there, the velocity would look something like this, because it's tangential to the path traced. Okay, now suppose we were to zoom into a different frame, that is, we were behind this car. What would we observe? What would we see as far as forces are concerned? And this is the purpose of the next slide. In the next slide, we're going to begin to apply Newton's second law in this case. Alrighty, so this is what we would see. Suppose this were our car and we were following behind the car. This is a slice of the road. So this is the flat surface, which I've indicated by the dotted line. The solid line is a picture of our ramp, and we are following this car from behind. Now, what forces are going to be present acting on the car? Well, because the car has mass, we know there's going to be the force of gravity, that is the earth attracting the car towards its center. And by virtue of being supported by the ramp or by the incline of the road, in the banked road, the car is going to experience a normal force. And depending on the state of things, if there is friction, friction will either be up the incline or down the incline. And then the purple lines represent the coordinate system, which I have selected, and which I encourage you in the context of uniform circular motion or banked curves. Whenever you're dealing with bank curves, it is wise, of course not limited to, but it is wise to choose an upright coordinate system. This will make your job a lot easier. Now, depending on the context of the situation, if there is friction, there could either be friction pulling the car up or friction pulling the car down the ramp. This friction here will exist if we are seeking to find the maximum speed at which the car can go around the bend. In other words, what's the maximum speed that the car can maintain without sliding away from the center? Remember, sliding away from the center would mean increase the radius. In other words, the car would be tracing a larger circle than the track. So the point is the car would move away from the center, would have a tendency of moving away from the center, which means friction would be acting down the incline. So the black arrow here is an arrow which represents friction when the car is driving at a maximum speed. But remember, that's not the only context we could have. Suppose the car is driving around at a slow speed. If the car drives at a slow speed, the force of gravity, or this component of gravity, can possibly take over, causing the car to fall in toward the center. In other words, the car will slide off the road this way. So this friction here would correspond to the minimum speed the car needs to maintain in order not to fall into this side of the road. But for this video, I will not treat friction. I will simply treat the case where there is no friction. So for our purposes in this video, I will not consider these two forces. Okay, so then let's apply Newton's second law in this situation. Newton's second law is going to take this form. That is, along the y direction, we're going to have the net force in the y direction causing an acceleration in the y direction. That's the I think the most intuitive thing, that forces acting in the y direction can only affect motion along the y direction, and forces in the x direction can only affect the motion along the x direction. But in this case, our y direction corresponds to either the car lifting off the road or digging into the surface of the road. And we want neither of those. So that means our acceleration in this case is going to be 0. This enables us to say the sum of all the forces, which is what the net force means, the sum of all the forces acting in the y direction are going to be 0. What are those forces? Well, there's a component of the normal force that's parallel to the y direction. And if you were to consider this triangle up here, that component is going to form the adjacent side of that triangle, which means the appropriate trig ratio is going to be the magnitude of the normal force times cosine of theta. This would be the y component of friction. And the other force that exists here is going to be the force of gravity. Notice the force of gravity points in what we've designated as a negative direction, so we will preface it with minus, with a minus. Then that's Fg. And then this will be equal to 0. Then we can say that the normal force in this case is going to be given by Fg divided by cosine of theta. So this is what Newton's second law reduces to in the y direction. What about the x direction? Let's consider the x direction. In the x direction, what we know is that there is going to be a component of the normal force which is parallel to the x direction. And notice this side is going to be the side opposite to this angle. So that means F net in the x direction is going to be the mass times the acceleration in the x direction. And the only force that's present in the x direction in this case, when we don't consider friction, is going to be wrong instrument, Fn times sine of theta. This is going to be equal to mass times the acceleration in the x direction. But remember, what is this direction? This is the direction which is toward our center. This is the direction we have designated as the direction of centripetal acceleration. So in the x direction, the type of acceleration we have here is centripetal, which means what we're going to have here, we can replace this acceleration with v squared over r. This is going to be v squared over r. Okay. And then from here on, we can use this fact here, that Fn, the magnitude of the normal force, is equal to the force of gravity divided by cosine. Substitute this fact into this equation. What we learn from here is that sine of theta times the force of gravity divided by cosine of theta is going to be equal to mv squared over r. Now these two are going to combine to give us tan theta times mg, because that's what the magnitude of the force of gravity is. It's equal to mg. And then we're going to have mv squared over r. And then we can essentially cancel these two guys out and learn that the speed that the car needs to maintain in order to go around such a turn is going to be given by r g tan theta, the square root of this. And I should say that this is the maximum speed that the car should maintain in order to go around this turn. Notice here that one of the key things is that we didn't have friction. What would things look like if we had friction? Let's consider the case where there is friction. And maybe let's consider the case where, again, we are seeking the maximum speed that the car can go around, can drive at around this turn when there is friction. Okay, so we're going to have to delete all of this in order to talk about the situation where there's friction. Well, if there is friction, notice now there's going to be a couple of forces in the x direction and in the y direction. I should mention something important here, that this angle here is going to be theta. You can convince yourself using a couple of 90-degree angles, because remember, this makes a 90, which means this angle here is going to be 90 minus theta. But the normal force also makes a 90 with the ramp, or with the frictional force, which means the angle here must be equal to theta. You can convince yourself. If not, please post it on a comment. I'm happy to explain it thoroughly. Okay. Alrighty, so then let's apply Newton's law in the y direction and in the x direction. I'm going to start off with the y direction, because the y direction, I know there's a bit of simplification since we don't want for there to be acceleration, so that would help a lot. Okay, so in the y direction, what we learn is that there's going to be the component of the normal force that is parallel to the y direction, so that's going to be Fn cos theta. There's going to be the force of gravity. But notice now, friction here has a component that is in the y direction. And notice it will point in the negative direction, negative y direction. So we're going to have minus Fs max. That's going to be sine of theta. And this is going to be equal to the mass times the acceleration in the y direction. But remember, we want the car to stay on the road, not to fly off, not to dig into the surface of the road. So this should be equal to 0. And then let's clean this up a little. Specifically, I have in mind that we need to unpack what Fs max means. Fs max is equals to mu s times the normal force. So we rewrite that, and we say mu s times Fn times sine of theta. This, and what I'm going to do now is I'm going to take this Fg to the other side. This is going to be equal to Fg. And you probably can see where I'm going to go with this. Fn is common to this, to both these terms on the left, so I could pull out the normal force as a common factor. And what is it that remains? What remains is cosine of theta minus mu s times sine of theta. This is going to be equal to Fg. And if we want to make this a little easier, we can say this should be under here, just to save space. Okay. So this is what we learned, that the magnitude of the normal force is going to be equal to the force of gravity, the magnitude of the force of gravity, divided by what's in the parentheses, cosine of theta minus mu s sine of theta. Now, this is what we've learned from the y direction. What would happen if we were to consider the x direction? The x direction I usually leave for last because, well, maybe I shouldn't say the x direction. I would say the direction along which there is centripetal acceleration, I leave for last. Because that's the one that usually has a non-zero acceleration, so things are a little more complicated. So let's go now consider that direction, which in our case is the x direction. So what we have, what forces are acting in the x direction? Well, there's going to be a component of the normal force that's parallel to the x direction, but there's also going to be a component of friction that has that is parallel to the x direction. And those are the only forces in this case that will be present. Then let's do like we did and apply Newton's second law. Newton's second law tells us that we're going to have Fn sine theta. So that's the x component of the normal force. And the x component of the frictional force, that's going to be plus Fs max cosine of theta. Since those are the only forces in the x direction, we can say they are the ones responsible for the acceleration in the x direction. But what kind of acceleration is in the x direction? Well, that is the centripetal kind of acceleration. And we know that's given by v squared, the speed, squared divided by the radius of the turn in question. Let's do exactly the same thing we did in the context of the y direction, and let's unpack what this means. This is nothing more than mu s times Fn, which means we're going to have Fn sine theta plus mu s Fn cosine of theta. This is going to be equal to m v max squared over r. And notice here, Fn again is a common factor. Fn is common to these two guys, so I can take it as a common factor. And for the sake of space, I am going to delete it over here and write it as a common factor, like that. This is just for the sake of space. I don't want to have to page to the next, to go to the next page. Now, we can use the little fact we learned earlier, which tells us that the magnitude of the normal force is equal to the magnitude of the gravitational force divided by this parentheses. So instead of Fn, we could simply plug this thing in there. Let's do that. If we were to do that, what we will find is that sine of theta plus mu s cosine of theta divided by cosine of theta minus mu s sine of theta. This is going to be, I forgot Fg here, Fg, this is going to be equal to mv max squared over r. And I believe from this point on you should be able to conclude that v max is going to be the square root of r times g sine theta plus mu s cos theta divided by cos theta minus mu s sine theta, all under 1 square root. This is the maximum speed at which a car can go around a circle or a corner with a radius r and an angle of bank mu s, and where the surface of the road has this much roughness. That is the coefficient of friction. Okay, I will stop the video here to avoid it being too long, but any questions, please post them in the comments and then I'll address them. Okay, see you in the next video.